Okay, so now we are just going to be doing determine whether this is convergent or divergent. To me, this looks like the problems that we were doing when we were doing the ratio test, because we know that when we plug in n+1, we can get a lot of terms to cancel, especially terms that have exponents, or terms that have factorials. So with all of that knowledge, I think the ratio test is the best one to use in this example, and the professor also used the ratio test for this one. So I think it's just a good one to use. So we'll just plug in n+1 to both. So this would be n+1 squared. All right. And then I believe we're actually going to need to do a little bit of algebra here. So we'll do it over here to save me some time. This is actually going to be e to the n squared plus 2n plus 1. And that is because I need to FOIL those guys out. So that's what that ends up being. So if I plug in, I guess we'll go there. If I plug this in, if I take my limit as n approaches infinity of the ratio of these two guys, so I will say n+1 factorial over e to the n squared plus 2n plus 1 over n factorial over e to the n squared. Complex fraction, so I can multiply by my reciprocal. So that will end up being limit of n+1 factorial over e to the n squared plus 2n plus 1 times the reciprocal, e to the n squared, and then this will be n factorial. All right, so with our factorials, we understand that a factorial by definition is going to be numbers one less than whatever that number is, multiplied by each other all the way down to 0. So to get these factorials to cancel, I can rewrite this as n+1 times n factorial, because n+1 is 1 greater than n, so this will be n+1 times n minus 1 times n minus 2, so on and so forth. So I can actually set that up so that that will end up canceling with my n factorial in my denominator over here. Very nice. And then I can do a very similar thing. We understand that our exponents are going to be, whenever we have things that are added in our exponents, I can split them up and rewrite them as the same base multiplied by each other. And I'm doing that because I have an e to the n squared, and then I have an e to the n squared, so those would actually end up canceling as well, which is very nice. So what I actually end up with is the limit of n+1 over e to the 2n plus 1. All right, so here it's a little more involved than our previous examples. In our previous examples, we were just able to divide by the highest power of n in our denominator and all the terms. But here we don't really have a highest power of n because we have n in our exponent. So we are going to utilize L'Hopital's rule, which just means take the derivative of the numerator and the denominator. The professor rewrote these because whenever we take the derivative of things, it's normally a function or a function of x. So that is why the professor took this step to rewrite this as a function of x. I don't know in the math world if that's needed. I assume it is because she's very diligent about her notation, but that is the reason why she's doing that. So she does a fancy symbol for the L'Hopital's rule, and then limit as x approaches infinity of Derivative of this, derivative of x is just going to be 1 over derivative of this, we're going to have to use chain rule. So it's going to be the derivative of my exponent times just the derivative of the whole thing. The derivative of e to the x is e to the x. So this will just be 2x times e to the, or no, excuse me, this is just 2. 2 times e to the 2x plus 1. And if we take the derivative, or excuse me, the limit as x approaches infinity, x in our exponent is going to get bigger and bigger and bigger. That is in our denominator. Our denominator is going to get bigger, which makes our whole number smaller, which means that this approaches 0, which is less than 1. And that satisfies our ratio test. So this series converges by the ratio test. Sound good? All right. Can't answer, so I assume it's good. Again, let me know. If not, and we can always go into these in more detail at a later date. Okie dokie. So now we are going to do, that was number 37. So now we're going to do number 42. Oh, I was like, how many more pages do I have? I have quite a few more pages. Quite a few, so we'll see how we get through all of this. So, number 42 is going to be determine a power series representation of the function 4 over 1 plus 4x squared. All right. So our base power series representation that we've been utilizing, not base, but I guess our most standard, is 1 over 1 minus x equals the sum as n equals 1 and goes to, or equals 0 and goes to infinity of x to the n. This, did I write this down wrong? Yep, I did. This whole thing is squared. Normally, it doesn't really matter what this number is because we can kind of move things around. So if this was just 4x squared, we could actually kind of just work with this and plug it into our function. But since this is a binomial squared, we would need to FOIL this, and that would end up with a completely different form than one that we are used to in this form or setting it up with this series. So what we need to do is we actually need to integrate this guy. That is the best way for us to get this to look like this. Because this, if we rewrite this function, this will be 4 times 1 plus 4x to the negative 2. Whenever we integrate, we add 1 to our power, or our power rule. So when I add 1, that's going to be negative 1, and that is going to go back down into my denominator, which mirrors this form over here. So this is basically a trick because we've worked with taking derivatives and integrals of our series. So you can mess with these and use our derivatives and our integrals to our favor so that it matches forms like this. So we can utilize this function. So I'm actually going to integrate this guy. So if I integrate, I get, my brain isn't working today. I'm going to get this plus 1 divided by that. So this will be negative 4 divided by negative 1. And then this will be 1 plus 4x to the negative 1. And then we still need to multiply or divide, excuse me, by the derivative of this, because what we are actually doing in this step is we are doing chain rule. We're not going to go through it just because time. If I set my u equal to this and took the derivative of it, that would be 4. And then I would need to divide by 4 when I do my u substitution. So I need to divide by whatever is the derivative of whatever I'm setting my u equal to. So how she writes this is she says the integral of this is going to be this guy, and she includes this d dx as basically like a reminder where once we end up getting it into our series form, we are still going to need to take the derivative because we ended up starting with taking our integral, and then we're going to need to take the derivative of it. All right, so I will rewrite this with some cancellation and moving this down, so our 4's cancel, and then this would need to get moved down into our denominator. So this would end up being negative 1 over 1 plus 4x. And this looks a lot more like this form, which is lovely. We are a fan of that. So I can rewrite this. I need a subtraction. I can rewrite this as 1 minus negative 4x, so that I have my minus sign here. And then, because I have that, all I need to do is utilize this formula. I have a positive 1 here and a positive 1 there, so I'm actually going to write this as negative 1 times negative 4x to the n, as n goes from 0 to infinity. And I still need to take my derivative of this guy. All right. Hopefully we're good there. It's always good to distribute our exponent because it definitely helps with not missing anything. So we'll say, still need to take our derivative. Negative 1 times negative 4 to the n and x to the n. All right. And then I shall take the derivative. So this will be, this is a constant, this is a constant, this is going to be my thing that I'm taking my derivative to. I need to subtract 1 from my exponent, and then I need to multiply by whatever that is minus 1. I'm getting my integrals and my derivatives messed up. It's the other way around. I need to drop down my n, multiply it by n, and then subtract 1. That's the correct answer. There we go. So now I'm going to actually split all these up so I can make my form a little bit better. Here I have a negative 4 to the n. This is technically negative 1 times 4 to the n. So I'm going to say this is negative 1 times negative 1 to the n times 4 to the n times n times x to the n minus 1. And then here I have negative 1 to the 1, negative 1 to the n. I can clump these together. All I need to do is add my exponents. So this will end up being negative 1 to the n plus 1 times 4 to the n times x to the n minus 1. And I believe that is her final answer. Let me triple check. This was number 42. Yep. Negative n, negative 1 to the n plus 1, 4 to the n times x to the negative. or n minus 1. Yes, definitely a loaded problem, and it gets a little funky down in here, but I'd say the process isn't super crazy. I feel like it could get worse, so yeah, hopefully we're feeling okay about this one. So it's knowing, oh, if I take the derivative of this could actually make my life a whole lot easier. So it's using that. I think we actually kind of do the opposite in a couple problems. So we will just keep going. All right, so number 44. Oh, you didn't have me do number 44. Number 45. Right, so number 45. Oh, because it was used the result of this. Oh, because, all right, I understand. All right, so if we have a function arctan of x, what is the radius of convergence if we do the power series representation of this? So we're actually going to be doing something very similar to what we just did. If we remember that if we take the derivative of arctan, I'm writing integral because if we were to take the derivative of this, then we would get 1 over 1 plus x squared. And what we would need to do, since we just start off by taking the derivative, again, we want the form 1 minus x in our denominator or something else in the place of x so that we can plug it into this series representation. And arctan doesn't look like that at all. But this kind of looks like this because we have 1 over 1 plus something. We can do the same thing that we did last time. We could say 1 over 1 minus negative something. And then that is what we can then plug into that power series representation. I'm going to keep needing to write my integral basically as a reminder that I need to keep or integrate once I actually get that power series representation. I didn't even notice that it was already done in number 44, so we'll just go through it because it doesn't take too long. So we'll say the sum n equals 0 going to infinity. It's going to be negative x squared to the n. We'll do the same thing. We'll distribute our exponent of n for each thing that is getting multiplied in there. So we'll say negative 1 to the n times x to the 2n dx. Sorry, there's just a child playing a recorder in the background. It's very distracting. So what I can then do here is I can integrate. I can add 1 and then divide by my new exponent. So right over here, then I have n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, and then I'm going to divide that by 2n plus 1, and that is going to be my series representation. Nice. And then whenever we do ratio, we can do the limit as, or whenever we're testing our radius of convergence, we do the ratio test, which means we need n plus 1, or a sub n plus 1. So my a sub n is this guy, so my a sub n plus 1 is going to be -1 to the n plus 1, x to the 2 times n plus 1 over 2 times n plus 1 plus 1. I can take the limit as n approaches infinity. I'm going to skip the step of writing the complex fraction, and I'm just going to put my n plus 1 here. Since we've done so much of this, just for the sake of time, I'm going to split up my things. I'm not going to write all of that out, because this is -1 to the n times -1, x to the 2n plus 2 plus 1, and I have a x to the 2n plus 1 here, so I'm going to write this as x to the 2n plus 1, and then times x to the 2, because that's x to the 2n plus 2 plus 1. So those are equivalent. Over, actually, I'm not going to be able to cancel this guy out because we have things added together in our denominator. So these, because they're not multiplied, will not be able to cancel. So I'm just going to FOIL or multiply this, distribute, and that would be 2n plus 2 plus 1, which equals 2n plus 3. And then I'm going to multiply this by the reciprocal because, again, this would be a complex fraction when we do our ratio test. I'm just skipping writing that step. Over -1 to the n, x to the 2n plus 1. All right, and then here, our -1s to the n's cancel, our x's to the 2n's plus 1 cancel, and we are left with the limit as n approaches infinity of -1 times x squared times 2n plus 1 over n 2n plus 3. Cool. And then we can divide by our highest power of n here since I have some n's floating around. Going back to our algebra, whenever I do this, since I have these things added and this just divide or multiplied over here, I need to divide by each term. Each term is something that is added or subtracted to each other. So I actually only need to divide these two terms in here and these two terms in my denominator. I don't need to divide by negative or divide by n. I don't need to divide -1 times x squared by n, since I'll be doing it for these two terms here. And that's just our basic algebra. If you had 1/2 times 4 plus 6, you would just divide each term by this guy. If I had 8 times 1/2 times 4 plus 6, I wouldn't divide 8 by 2 and 4 and 6. I wouldn't do all of that. I would just do 4 divided by 2, 6 divided by 2, and then that 2 would go away, and that would be complete for that operation. Work that out. My brain isn't really working today. But I just need to do -1 times x squared. Highest power of n is just n, so this is actually going to be 2n divided by n, or 2 plus 1 divided by n, over 2n divided by 2, or 2n divided by n is 2, plus 3 divided by n. If I plug in infinity, these fractions go to 0. So this actually ends up being 2 times -1 times x squared over 2. Right? Is that what I got? Yep. And then those 2's end up canceling. What is our question. What is she asking? This is number 45. What is the radius of convergence? Since I just have negative x squared, and that needs to be less than 1, since I don't have this multiplied or divided by any specific number, my radius of convergence would just be 1 in this example. Sound good? We've gotten a lot of ones. Had a lot of this in our previous problems that we've gone through. But yes, it is, again, very similar to the last problem that we worked through. Knowing what this goal is, knowing what we need that to look like, and thinking, can I derive this and get it to look like that form, or can I integrate this and look like I can get it in that form? And whenever you do that, you just need to remember to go the opposite way when you actually get the series representation set up. Then you would need to do the opposite of whatever action you did initially. So it's kind of like a trick. It's kind of nice. Alrighty. So I'm at 25 minutes, so just to kind of keep the videos short and not super cramped, I'm just going to upload this one and then keep going with the next one.